He has consulted with mining firms and now works as an electrical engineer for a local cooperative. He is an avid cryptocurrency miner who enjoys researching financial and transportation electrification, peer-to-peer systems, and the electrical grid. It is my great pleasure to announce Tyler Bain.
Thank you. I think, so the goal with this presentation is to kind of just put some tools into all of your hands to kind of attempt to estimate the network consumption on a handful of different algorithms for some popular proof-of-work cryptocurrencies. There's some pens and papers up here. I think at one point we might try to have y'all churn through some of the math yourself, but also a spreadsheet or a phone calculator would be adequate as well. And so I think the goal is to talk about a couple of the different methodologies of determining the electrical consumption on a handful of different algorithms. Also go over some of the basic tools you would need to acquire that data and fully understand it. And then also look at some of the upstream manufacturing costs of ASIC mining hardware. And so we'll start off with just a couple energy basics in terms of like the mining industry. So a unit that it's thrown around quite a bit with regards to ASIC energy consumption is the joule, which is essentially just a unit of energy, work, or heat. It's an international system of units, like an SI unit. It's derived. It's not one of the base units, but it can be described as a Newton meter, a kilogram meter squared per second, and then it's also a watt per second. So that's crucial later on when we're doing some of the math. You can convert directly from joules, a unit of energy, to a unit of power, watt, by dividing it by time. And so typically in energy consumption realms, efficiency is described as useful output divided by total energy input. And it's in the computational realm, it would be described as like performance per watt. And so sometimes you'll see like flops per second per watt or operations per second per watt. However, in the mining industry, a lot of these manufacturers will specify their equipment as energy input over useful output. So almost the inverse of what like a traditional efficiency calculation would be, but it does essentially provide the same result, just a benchmark of how much energy per useful output. And so for an ASIC example, you'll often see manufacturers rank them in terms of joules per hash per second. And typically not just hash, it would be one of the magnitudes of a hash. So joules per terahash per second or joules per megahash, depending on the algorithm. So those are some key concepts to know. Another topic that I think is widely misunderstood in the electrical realm is power versus energy. So power is just the instantaneous consumption value measured in watts or derivatives of watts. And so typically you would see a light bulb might be rated at 60 watts. That's how much power it would consume any given instant. Whereas energy would be that power curve integrated over time. And so energy would be has the time component included in it. And so the units for that would be watt hours or kilowatt hours. And typically in the mining space, you'll see benchmarked over terawatt hours. And so that can be, I tried to visualize it real quick in a quick graph. So this is a logarithmic scale, but the blue line here, the watts, is the instantaneous consumption of, let's say, an Antminer S9. It's about 1,300 to 1,600 watts, and that would be constant if you were mining over, say, a 24-hour day. And then the amount of energy that would use over that same day is really the area under that curve, in this case a line. And so as you can see, over a 24-hour period, it would consume steadily more energy each hour that you're consuming that power. And so it gets back to that key difference of energy and power. Another important chunk of data to know for some of these calculations is just the typical SI unit prefixes. And so here I have it listed in hashes, but watts, any other SI unit, and also derivatives of those units can be expressed in this notation. And so typically a miner would consume in the order of magnitude of a kilowatt, 10 to the 3 watts. Whereas the Bitcoin network today is in the amount of hash rate on the network is in the order of the exahash, so 10 to the 18 hashes, about 80 exahashes these past couple days. And theoretically, you could go even higher into the zeta or iota hash magnitudes. And so I think one thing, we often see articles that are widely cited quoting, extreme amounts of electrical consumption based on proof of work mining. And I think the big misconception is how those numbers are derived. The most widely cited source I've seen over the past 5 or 6 years is this, it's sourced from this Digiconomist site, and they perform an economic-based calculation. And so essentially they're asking, with their calculations, how much can miners afford to expend in electrical power and derive it from that, which, if you're looking at it's derived essentially from the price of Bitcoin or other cryptocurrencies, and with the wide fluctuations could lead to pretty extreme varieties in that proof of work energy consumption calculation. So if the price doubles, does the energy the network expend double? Maybe, but most likely not. It's looking at different variables. And so if the price decays by 50% or 80%, does the network energy consumption also decay at that magnitude? I would argue absolutely not. So I think there's some big flaws in the economic-based calculation energy consumption methodology. And so I would propose, and a lot of others have actually followed up on this calculation over the past 12 to 24 months, I would argue a physics-based calculation is more accurate and firmly rooted in on-chain data and scientific international units that are more easily digestible and derived from real life data. And so the economic calculation starts at how many Bitcoin are created per day, and what is the dollar valuation of that Bitcoin, and then from there they also estimate global cost per kilowatt hour, which is also problematic because electrical prices, even just in the US, vary widely, anywhere from 4 cents a kilowatt hour to 30 plus. And so that is a pretty gross assumption to make, in my opinion, and then they take that amount of value and then multiply that by an estimated operational expenditures of mines on electricity, which is also problematic. Some of the energy could go to something other than mining, and oftentimes most of that value isn't going directly towards electricity, but this calculation assumes that. And then they derive a kilowatt hour per year value from that. And so with the physics-based calculation, we look at the amount of blocks that are created per day or over a 2-week period in each difficulty adjustment realm, and you can estimate a network hash rate based on that difficulty. And so from that network hash rate, you would then compare the efficiencies of that hash rate to attempt to derive a unit of joules of energy expended, and you can quickly convert that to power and energy per year. And so I kind of highlighted the areas where assumptions are being made in these calculations, and I think we limit assumptions quite a bit more in the physics-based calculation versus the economic-based calculation. Here, the main assumption we're attempting to make is the efficiencies of each one of these miners, which are subsequently published by a lot of these mining companies. So it's a little easier to estimate as opposed to just assume. And so from there, the first variable we're looking at here for the physics-based calculation, we'll walk through that process. One of the variables is that network hash rate. And so for maybe 5 or so of the more popular proof-of-work algorithms, and then the dominant mining chain on as far as hash rate for each one of those algorithms. I compiled essentially a network hash rate for each chain. And so this is also logarithmic, and this is as measured in terahashes per second. So we've got Bitcoin, Dash, Litecoin, Ethereum, and Zcash. And this also speaks to relative network security for each of these networks. So based on those estimations on the block rate, the block emissions rate, we can pull out that hash rate. And then so I went through the process of attempting to estimate that efficiency of each ASIC miner mining towards these different chains. And so for Zcash, the proof-of-work algorithm is Equihash, and they actually have about 7 or so popular, profitable ASIC mining rigs on the market today. And the unit of efficiency that these manufacturers specify is joules per kilosolution per second. And solution on the Zcash network is very similar to hashes. It's kind of a different nomenclature and slightly different, but essentially it's an attempt on finding that block. And so the average, the best way I could think of estimating it is assuming each one of these miners has essentially an equal contribution to the network. Chances are this is also incorrect, but less incorrect than the other estimation methodology. And so right now, the state-of-the-art Zcash ASIC mining equipment is around 15 to 17 joules per kilosolution per second. And an ASIC mining rig is an application-specific integrated circuit computer that's just designed specifically for mining. I also did the same kind of calculation for Litecoin, which is running the SCRYPT algorithm. And so on average, the Litecoin miners are quite a bit more efficient than the Zcash miners, just in terms of joules per hash per second. And the unit here is also megahashes. And so kilosolutions for Zcash, and then megahashes per second in terms of joules for Litecoin and SCRYPT. Also did that same kind of like equipment study for Ethereum, for ASIC mining efficiency. And so ETHASH is their algorithm, and they do have a handful of ASICs deployed. And interestingly enough, the SCRYPT miners are on average just a little bit more efficient in terms of work output and energy input than the ETHASH Ethereum miners. And are right around like 3 to 4 joules per megahash per second. Did the same calculation here for X11, which is the Dash proof-of-work algorithm, and their efficiency benchmark averages out in joules per gigahash per second, and that's around 30 to 40. And chances are, looking at this graph, most likely all the miners do not belong, this would be a smaller percentage of the network, and then also the most efficient ones might also very well be a small percentage. So I think the best way to attempt to estimate it is to just kind of do like an average of what those energy expenditures per hash out rates are, just based upon the different ASICs deployed. And I think it's interesting to look at the Ethereum ASIC development versus the quantity of ASICs that have been deployed on like X11. It seems to be a little bit more popular as far as mining equipment manufacturers. And then this is that same kind of graph done for Bitcoin, the SHA-256 algorithm used by ASICs for mining. And this is, again, another order of magnitude more efficient, as it's measured in joules per terahash per second. And this is just a quick audit of most of the popular machines available on the network to be deployed today. And they range anywhere from 160 to about 40 joules expended per terahash output, with around an average between 80 to 100. And this is all of those previous averages plotted against each other, looking at average ASIC efficiency by algorithm, normalized into joules per terahash per second. And so you can kind of see the ranking of efficiency based upon algorithm that some of these ASICs have been deployed upon. And so, SHA-256 would be, the most it has the most efficient hardware deployed on it in terms of electrical consumption and hash output. And Equihash, interestingly enough, Zcash doesn't appear to be as popular for miners or mining equipment manufacturers to deploy hardware onto. And this is kind of attempting to bring all of those statistics together to calculate out those energy consumption levels and power consumption levels. And if you guys want, this is a perfect opportunity to test out the calculation yourself. I figured maybe a little hands-on math might be worthwhile. The big trick here is just making sure your units are correct upon doing the calculations. And so essentially, just walking through the calculations, you would want to take the average efficiency in joules per terahash per second and multiply that by the overall hash rate as estimated by the block emission amount. And that kind of thinking of it in terms of like chemistry, it's a unit conversion problem, really, almost along the lines of stoichiometry. And so to eliminate to get rid of the terahash per second on the bottom of this average efficiency equation and just convert it to joules, you would have to multiply it by the unit terahash per second to get rid of it. And so that would give you a pretty decent estimate of joule energies per second. And then you can convert that to power, essentially 1-to-1 watts to joules. And then you could take that instantaneous power consumption and multiply it by the amount of hours in a year to estimate the terawatt hour consumption. And so we do that, we pull that all together in the next slide, and this gives a relative amount, I would argue a more accurate estimation of network power and energy consumption. And so the power consumptions on these networks range anywhere from 100 megawatts down at the Zcash level to upwards of 7 gigawatts on the Bitcoin network. And those equivalents, energy, taking that power and projecting it out for the entire year, which I also would argue is a pretty dubious calculation to make, taking an instantaneous power projection and just assuming that stays constant for the entire year. That you're taking quite a bit of assumptions. We all see how fluctuating the hash rate is on these networks. It's changing, every day, every block essentially. And so, however, that it does seem to be the way that a lot of these sources compare these energy consumptions is over a yearly basis, as opposed to estimating it instantaneously on the power consumption. And so that comes out to be just under a terawatt hour a year for Zcash and upwards of 62 terawatt hours per year on the Bitcoin network and anywhere in between for the other three. And so I decided to graph that out. This is also logarithmic, looking at power in terms of gigawatts and yearly energy in terms of terawatt hours per year. And you can kind of see the vast differences in each of these networks as far as in like a visually digestible manner. And so I wanted to kind of compare how that estimation method compared against other folks that have also done this calculation and plot them over time. And so some of the earlier estimations were around December 17, as far as in like the current era of Bitcoin mining. And so we've got like this dashed line in the middle shows kind of the rolling average of those terms. And then and that's plotted in terawatt hours per year. And then this solid line is the network hash rate in exahashes per second. And so as you can see, we're nearing, I think now that we might be just above 80 exahashes per second. This was made sometime last week. And so interestingly enough, the calculation we all just performed on the Bitcoin network is very similar to the trend line for the calculations of all these other folks. And this kind of shows their timing as far as and it does seem to trend with network hash rate, which it should. And interestingly enough, this outlier, this Hasma-Cook fellow, he has an incredible calculation methodology, and he takes into account in his calculation not only just direct electrical energy consumption, but then total energy consumption inputted into the electric grid for that output on the electricity. So his has a couple other inefficiencies added in, and he also adds in the equivalent, the amount of energy that's required to create the hardware itself. And so we're going to go through that part next. And so this is actually cited from that same Hasma-Cook fellow, and he estimates that each ASIC mining rig costs about 895 kilowatt hours to manufacture it. Everything from semiconductors to transport and packaging. He really did his homework on this calculation, and so I figured I would cite his total energy consumption is in terms of manufacturing costs on the energy side. And so taking that number and trying to estimate the amount of ASIC rigs on each one of these algorithms and mining towards each one of these chains. The way I thought would best be to do that is to take the network hash rate, the total hash rate, and divide it by the amount of the average ASIC hash rate output from those previous ASICs that I cited in those graphs. And so this is in terahashes per second, and so Zcash is still in the kilosolution range, and so they're quite a bit lower in terms of total hash output than, say, like the average Bitcoin miner would output about 28 or 30 terahashes per second. And so this gives like a fairly decent estimation, in my opinion, of the amount of ASICs on mining towards each chain. Bitcoin has about 3 million, and Zcash has about 62,000, and ranging anywhere in between. And so that this calculation, as far as terawatt hours, would assume all of these ASICs are produced, this year, essentially, which is also, kind of a steep assumption to make. And so this is these results graphed against the mining consumption per terawatt hour per year. This includes the manufacturing energy of all the ASICs on the network. And most likely, all of the ASICs currently running were not produced in this calendar year or this rolling 365 days. And so this is it just graphed on a normal scale, but I thought the logarithmic scale gives it a little more detail as far as the breakdown between manufacturing energy and mining energy. But really, it shows that the majority of this consumption from mining doesn't actually come from the production of the equipment, but the operation of that equipment. And then I thought it would be handy to compare that estimated electrical consumption in terms of terawatt hours per year against a handful of things that we might be more relatable to. And so yearly, the U.S. in a period of a month or two consumes just under 10 terawatt hours a year for Christmas lights, to light up homes. And then I thought it would be interesting to cite the amount of energy that's inputted into fiat currency printing each year, quite a bit less than cryptocurrency mining. Cryptocurrency mining, and these altcoins here, that's actually just the 5 we just discussed. And this includes the manufacturing energy of those ASICs. And so altcoins here is kind of a misnomer. It's just those 5 we looked at. And gaming, I assume this is PC and console gaming over the globe in any given year. And mining consumes just over what the state of Colorado would consume on the electric grid over a year period, according to the Energy Information Association. And then these 2 on the left, I think maybe hit near and dear to all of our hearts, is gold mining, which is a very energy-intensive process, and then also just the cumulative consumption of the banking system. And this is also global. This will include the heating, ventilating, and air conditioning of banks and different branches, and also the consumption of armored vehicles, to transport currency. And so just looking at it in this scale, I think kind of puts it into comparison as far as what would be an ecological disaster and what wouldn't. And then this is a quick citation of some of the different sources that I used to compile this data. And I think that about wraps it up. Does anybody have any questions?
So I wasn't sure on your graph where you're comparing the different forms of calculation.
Yeah.
Did you compare it back to the initial, fiscal calculation that you referenced at the very beginning?
The economic calculation? Yeah, so that was part of it. And interestingly enough, that fellow the digiconomist guy, it's this Alex DeVeers, he's revised his calculations quite a bit. And so his is more in line with what I would say is fairly realistic. And that didn't happen until about 6 to 12 months ago, when some of these other calculations started really contradicting his conclusions. But prior to that, he was estimating 120 plus terawatt hours a year at a time where the network couldn't have even possibly consumed that, assuming really low efficiency. It just wasn't physically possible. But his now. Yeah, absolutely. And that's a lot of the articles that would come to mind for many of us in this room were cited on those calculations. And so I think that's kind of been a disservice, and there's quite a bit of sensational headlines associated with it that aren't really based in any real measurable physical unit. They're the economic calculation of how much could a miner afford to expend, and typically they're not expending that percentage of the operational expenditures on electricity, at least in my opinion. Yeah.
Would you see a significant drop in the energy consumption given how expensive ASICs are and yet how efficient they are?
Yeah, so that's a really good question. The trick with that calculation, I don't have it here, but you'd have to essentially estimate the joules per hash per second of, like, say, this laptop, which is possible, and we do have that data. I definitely, that would be an interesting comparison. However, today we're doing so much more work with orders of magnitude less electricity. And so it would be interesting, I would assume in some of those early mining days, it would be consuming more electricity than it would appear based on the hash rate, just because of the efficiencies of some of those older pieces of hardware. Absolutely. Yeah.
I have a quick question about how you got those numbers, the total ASICs for each of the coins and also the averages.
Yeah, so I just performed a quick audit. So I just compiled, I compiled as many ASICs as I could find publicly available, their consumption and output data, and just plotted them specifically. So this joules per terahash per second is really just taking their hash output and their energy expenditures and dividing the energy by the hash output.
No, I mean, there's another one where you say the number of each model. Where do you get those numbers? Because they don't usually publish those.
Publish what numbers?
If you go forward, you'll see there's one at the end where you say number. Yeah.
Oh yeah. So the
estimated count.
Yeah, so estimated count, and again, that is definitely an estimation, but the way I derived that estimation was taking the average hash rate of all of these plotted here. And so I don't have that graph, but I do have that data behind the scenes. And so each one of these, this is just an efficiency graph. Well, then I plotted out the hash rate output of each of those mining rigs, which absolutely is published, and then I took an average of that. And so again, it most likely is wrong, but it is an estimation. It's definitely within percentages of accurate, and so that's kind of an interesting question. And I wrapped my head around this a couple times, is how to estimate those number of rigs. And this was the best way I could think of with the given data, as far as just average output per mining rig, just based upon the statistics that the manufacturers publish, because we really don't know how many are running at any given time. You could probably audit each pool and see how many workers they have, and then compile that data, and that would be another approach to attempt to estimate it.
Because if you use like ASIC minor value or one of those sources, a lot of reported ASIC hash rates are for future machines, which don't really exist. So
Yeah, well, and these I believe all of these ones that I cited here are in existence and running. The most efficient one we've got here is the Antminer S17 Pro, which I believe is released and would be mining. This is based on the table up here, which essentially I just plotted these two right-hand columns in that graph. But those, I just derived them into units of equal magnitude, essentially. So hashes, and the big leap of faith I think I took in some of this calculation, at least on the Zcash side of things, is assuming that solutions and hashes are essentially equivalent, which, you know, depending on who you ask, they are and they aren't. I think this is an accurate or an accurate estimation of network energy consumption in terms of mining hardware inputs. However, that wouldn't account, the one thing I didn't account for here is node consumption. But typically, you know, you could run, say, a Bitcoin node on a Raspberry Pi that would consume anywhere from, you know, 6 to 25 watts, a really low amount, to actually process the transactions themselves and the blocks. You don't need a terrible amount of electricity. But with the mining itself is where some of that like arms race in electrical capabilities comes up from. So yeah, this is comparing, these are all these same units as far as gigawatts, terawatt hours per year. So I would think it's apples to apples in terms of energy and electrical consumption, but not, it's not normalized for transaction volume or coin throughput or any of that. Yeah, I think that would actually skew things even further for some of these coins that have much more value being transmitted based upon that consumption. Yeah. Yeah. Anybody else? Yeah.
Calculations based upon what it actually costs to use cash. I mean, because when you get cash, I
Totally.
through my fingers and I try to count it. I have to put it in my wallet, and all these little things that happen from my purchasing something to it going to the bank, and the convenience of you know, cryptocurrencies and base credit cards. When you get a credit card, you have to
Yeah.
the energy at every store to use the credit card thing. It may be negligible, but is it? Has anyone done those types of calculations?
I'm not certain. I should have tried to look up some credit card network estimations, but I would assume that might also fall underneath that banking system estimation. And another thing is, you know, we're all carrying around, let's say, a couple notes, and I think the average bill is about a gram, and so we're carrying around, depending on how much dollars are in our pocket. And so that requires energy, just our energy to transport it. And we see that come out in the banking system. We see that come out in the banking system's calculation as well, because they're forced to hire very heavy armored cars to transport notes from here to there. So I think part of that would be included in that, but like you're saying, that would be a very tough estimation. I think one of the reasons why Bitcoin and other cryptocurrency mining draws so much attention is because it is actually fairly easy to estimate that energy consumption, where some of those other networks, is, you know, credit cards or the banking system itself, it's a little bit more difficult. Yeah.
Kind of pro coin again, but gold mining, that's mining the gold. The cryptocurrency is also the processing of the transaction, so there's a lot more value
Totally.
in that.
Yeah, and gold mining, that's just mining. There's also like recycling and just the transport costs of gold itself, which are not in this, which would kind of be included in the cryptocurrency calcs. So
It changed my views because you see all those articles, and I really thought it was completely wasting
yeah,
energy, but it seems like actually there's
And-
some pretty efficiency.
absolutely. And you know, waste is kind of a subjective, you know, claim. You know, if energy is being put towards a purpose anywhere in society, you know, it wouldn't be wasted. And so obviously individuals are electing to contribute energy to mining cryptocurrency. So in their opinion, it's definitely not wasted, but I can see how others who might not totally understand the ins and outs of the ecosystem would assume that that's a waste.
Good analogy. Sorry, a good analogy there is the vehicle. I think I don't remember the stats exactly, but like 5% of the energy expended to move the vehicle from point A to point B, 5% of the energy moves the person. The other 95% is it wasted, or was it necessary to get that person where they need to go? So yeah, it is, it's very unfair, I think, the way the media portrays these things compared to when you really do the critical thinking on these things, and when you add the other values that you mentioned. I mean, it's so hard to see these articles, and thank you for doing
Yeah, absolutely. Jason?
Yeah, along those same lines, is there any way to kind of factor in, because a lot of these mining rigs are operated in cold environments?
Totally.
There's sort of a heating cost that is savings because of.
Yeah, and that's one thing. These calculations totally overlook heating, ventilating, and air conditioning. Typically, most miners would prefer to be in a cold environment so that they don't have to expend excess electricity to cool their rigs. But also, I'm familiar. There's a handful of miners that propagate in like the Texas area, very hot, climate, and they don't expend a lot of energy on cooling. They just exhaust it. So I think cooling costs would be tough to nail down as far as an estimation. But you could also reuse that energy in a lot of climates to then either reheat a business or a home or a warehouse or something along those lines. But yeah, these don't. This calculation assumes zero estimate. It kind of just ignores the heating, ventilating, and air conditioning. Cool. Well, thanks for all coming. Definitely appreciate it.